Hello and welcome to video lecture number 11, which covers section 1.7, day 1, rigid transformations of functions. By the end of this lesson, you should be able to graph a function using rigid transformations and be able to write a function given a rigid transformation graph. After reading the lesson title and the objectives, the first natural question is probably, what are rigid transformations? If you read through the information, you'll note that rigid transformations are graphs that have the exact same shape and size as their parent graphs, but they may be shifted to different locations. So if you take a look, you have the parent function f of x equals x squared, and notice the graph that is above it is the function x squared plus 2. Well, notice what the effect of this plus 2 is having on the graph. It means that we've shifted the graph of the parent up 2. These graphs are the exact same shape, they're the exact same size, but once again, the child is in a different location. If you take a look at the graph on the right, we have the same exact parent, but the child function is written as x minus 2 squared, and this minus 2 is an indication that yes, the graph has shifted 2 to the right, and this can be misleading because of the negative sign inside, but clearly what that is showing is the graph has shifted to the right. So using general function notation, if we take a look at the graph on the left, notice it is shifted up 2 from the parent, and what we can write is that the original function has had 2 added to it to shift it up. If you look at the graph on the right, notice it's shifted 2 to the right, but what we can say is that the original function has had 2 subtracted from the x. A summary of vertical and horizontal shifts is provided for you at the bottom of the first page, and I'd like you to take a moment to look at it. And if you take a look at the vertical shift, notice there's a constant that must be added to the function. And that constant is outside, quote unquote, of the independent variable. And we'll show you some examples of that coming up. If you take a look at the horizontal shifts, left or right, the constant value will be inside, quote unquote, next to the independent variable. And again, we will show you some examples of that. So this outside to inside relationship, you'll hear me saying a lot throughout this lesson and the next. Example 1 asks us to use the parent function f of x equals x cubed to sketch the graph of the given. Now, the first thing you need to do is plot the parent on the coordinate plane. And so I've done that for you here, and just to note, some of the key points will be 0, 0, 1, 1, and 2, 8. Now, since this is an odd function, you note that negative 1 is also on the graph, as well as negative 2, negative 8. So using this graph only, nothing more, not a graphing calculator, nothing of that sort, we will graph h of x equals x cubed plus 3. So the plus 3 written outside of the function, notice the plus 3 in the equation is not inside parentheses with the x variable, it is outside, indicates that we must shift the entire function f of x up 3. Essentially what we've done is we've taken the y values and added 3 to all of them. So if you take a look at the points that I'm boxing in, these are the points that belong on the graph h of x. So you do not have to write the information of the points, but I do be sure to have both the parent and the function h of x, the child, graphed on the coordinate system. So I will also try 1c with you now. So in example 1c, you are given the function q of x, and notice there is a number with inside the parentheses with x and a number outside of the parentheses So remember, the number inside is a left or right movement, and so -3, although negative means left, remember the minus is part of the formula itself, not necessarily the value of 3. So the 3 means move right, and the +2 means go up 2. So we do have two shifts going on here, and so I've shown you two specific points from the parent function, and in both cases I've moved both of those points +3 to the right and +2 up. You will do that with every single point to complete the graph. So I went ahead and did that for all points, and I've listed the points in large green letters here for you to get a better view. Once you have this completed, you are done. Now remember, the key is not to necessarily enter these functions on a calculator and graph them. The key is to be able to use the numbers in the equation to produce the graph by hand. So please take a moment and try example 1B on your own and have it ready to check for tomorrow. The other type of rigid transformation is known as a reflection. Now in this lesson we will talk about two types of reflections, those over the x-axis and those over the y-axis. Let's start with the graph on the left, which shows you the parent quadratic f of x equals x squared reflected over the x-axis. Now important to note is that when we reflect this graph over the x-axis, it is not the x values that change, however, it is the y values that become opposite. If you were to take the same parent function f of x equals x squared and reflect it over the y-axis, what you notice is you end up getting the same exact graph. That is definitely because this is an even function. So reflecting over that y-axis, take a look at the 2 points that I've labeled. It is not the y values that are opposite, it is the x values that become opposite once you reflect over the y. Now this isn't always the case, but any even graph that is reflected over the y will look exactly the same as what it began. So there's a summary of this at the bottom of the second page, and let's start with the reflection of the x-axis. Now again, this is corresponding to the graph above and to the left, and the notation reads h of x equals negative f of x. Well, if y is simply another symbol for f of x, then this is telling us that the y's must be opposite. So again, important to note, when you reflect over the x, the y's become opposite. So when you see a negative symbol outside or in front of the function, that is indication that there is a reflection over the x-axis. When we reflect over the y-axis, like we did in the graph above and to the right, notice that we can write f of negative x. And since the x is the one being opposite, that means that that negative value has been inside the function with x, and that is an indication that we have a reflection over the y-axis. Now we will take a look at some examples on the next page. Example 2 asks us to compare the parent function and use our knowledge of rigid transformations to write equations for the functions you see in Part A and Part B. So if you observe the differences between the parent and Part A, the first thing that you notice is that in order to see the graph in Part A, there must have been a reflection of the parent over the x-axis. So I will go ahead and note that underneath 2A. So if there has been a reflection over the x-axis, recall that the y values between the parent and the child must be opposites. So the way to symbolize that would be negative f of x. Remember, f of x is just a symbol for y. This indicates the y opposite values. The next thing I notice that in order for us to match the parent graph with the child, there must have been a shift in the parent graph up 2 units to make it match the graph that you see in red. So I've written that down, and the symbol notation for that is take the y values and add to them. So now our goal will be to combine these into an equation specific to the function g of x. So when I take these two rigid transformations and combine them, I notice that the function g of x is formed by taking the parent function and making the y values opposite and then adding 2 to the y's. Now by substituting the function f of x with its parent x to the fourth, we end up getting the specific equation negative x to the fourth plus 2. Now if you're concerned or questioning your answer, you can always graph the equation that you've written and make sure that it matches the graph that you see on the paper. So take a moment to try example 2b on your own and have it ready to check for tomorrow. The final example asks us to use the language of transformations to compare the graphs of each function below with the graph of the parent, and in this case our parent is the graph of the square root of x plus 2. You're supposed to name the transformations in the correct order, and because reflections are indicated by negative signs multiplied by x, we must name the reflections first according to PEMDAS, because multiplication comes before addition and shifts are represented by addition or subtraction. So let's go ahead and try example 3a. The only difference I notice in g of x compared to f of x is the negative sign in front of the square root. Therefore, we will write down the reflection that is associated with it. Since the negative sign is outside of the function of the square root, that must mean that the y values are opposite. Since the y values of these graphs are opposite, we can say that the graph of g of x is the graph of f of x simply reflected over the x-axis. So that would be the words we would use, and below that you see the symbols that we can use to indicate the reflection over the x-axis. So in example 3c, you're given the function for q of x, and notice I've rewritten it. Inside the square root we have x plus 4, but notice that can also be written as x plus 2 plus 2. And the reason I've done that is because I wanted the x plus 2 to be similar to the parent function. So there are three things then that are different from q of x compared to f of x. There's a negative outside, which indicates a reflection over the x-axis. There's a positive 2 inside of the square root next to x, so that indicates a shift left 2 units, and then the negative 3, which is outside of the square root function, indicates a shift down 3 units. So there are actually 3 transformations going on in q of x. Now we will write the symbols for that. So in general, you see the symbol notation reading q of x equals negative f of x plus 2 minus 3. Again, that means we reflect, or there's a negative on the outside of the function, and inside of the function we added 2 to x, so you'll see x plus 2 in parentheses, and then finally we subtracted 3 from the function on the outside. So please take a moment and try example 3b on your own and have it ready to check for tomorrow. This concludes video lecture number 11. As always, take a moment to look over what we've done and write down at least one question you have after watching the video lecture. Thanks for watching and good luck.